missing 2, so I think they'll be coming.
Yeah, that's my guess too. They are the ones that are usually a little tardy anyway. Everybody's champing at the bit.
Okay, this is the day where we make the connection with the quantum phenomena that we've sort of been touching on a little bit in the last lecture and earlier in the class when we did the beginnings of the connections to Lagrangian, Hamiltonian. So we're going to make a big deal of that right now. It would help, though, for me to just say a few things about what we did last time. In fact, the construction that I hope you've brought it along so you can work on it a little bit. This construction that involves the velocity, relativistic velocity of 3/5 the speed of light. We'll play with that just a little bit on the board here in a review of that. And the other thing that I want to talk about right off the bat, and that is the idea of having 2 lasers that originally were tuned or appeared tuned in their center of momentum frame, but then when you move one way, or as William has said, the other way, whichever way you move, you're going to be red shifting, increasing the frequency of the one you're coming toward, and you're going to be doing the opposite, that is blue shifting the one you're coming toward, making it higher frequency, and running away from a light that will now be downshifting, red shifting. The thing that I want to mention about that is a thought experiment that explains why we do that geometrically, and the idea of the ratio of the appeared source divided by the frequency at the source. That is the light that you view, say Bob views, and then Alice has tuned her laser to send the light, and then he's got a relative velocity with respect to her that's going to either make that light increase in frequency, blue shift, or if they're separating, red shift, reducing the frequency. So what I want to imagine is a thought experiment where, say, I'm Alice and I'm flashing to you. There are more men in here, so there's a lot of Bobs in here. There's only one female in this classroom. In any case, the idea is that Alice can fool Bob into thinking it's some other kind of light. Now, whatever it is, whatever the frequency she's holding and whatever the velocity is an important thing. The important thing I want to mention is what we did very first class when we talked about the perfect collisions, the ones that satisfy time reversal. Here, time reversal is involved. If I'm, first of all, in the real situation where Alice is projecting to you some light, and there's a Doppler shift, let's just make it a blue shift. So she's sending 600, you're getting 1200 because I'm coming towards you real fast, 3/5 the speed of light. Now think of the time reversal of that. The time reversal of that is, first of all, for me not to be coming towards you, but me to be backing up. Okay? And the other thing that has to back up is the light itself. So instead of having a source that goes into your receiver becomes the source, and I become the receiver. You see that? Okay. So in one case, the source, the receive over source, remember that was the ratio we're talking about, is one way, In the other case, it's flipped. So when we had a factor of 2 on one side of this pair of lasers that's making this diagram, one side has this at 1200, that's 2 times the starting frequency in the rest frame. That's this original baseball diamond. And then the inverse of that is this, because the flip. So time reversal is a very important part of the trading of light, which all of this involves. Okay, so what I want to do before we get to this derivation, this is a key thing, we'll spend the most time on this, a medium amount of time on going through the formulas that you've seen, but you haven't seen them coming out of wave mechanics. And then we'll talk about some things that aren't going to be anything to do with an exam. All of this stuff in that table, this particular table right here, we're going to have 2 tables that have identical entries with different physical names to the phenomena. That's the goal of this lecture that we'll spend the most time on. So first of all, though, let's make sure that when we look at these pictures, the things that we've been drawing, particularly this one, where Alice are receiving a light, he's also getting it from the other side, the fact of the ratio. But the main thing I want is to distinguish for one last time here that we have a diagram on one side that is the one we live in. That is, we've got space, and actually we have 2 more dimensions of that are being talked about here, and we have that 4th dimension of time. So on this side, the spatial axis, assuming that everything that we're interested in is just one dimension in space, and that's the situation here, we have here things that are keeping track of things that are links. And we have 2 kinds of frequencies, or 2 kinds of waves. Waves that are inside this, and I'm particularly pointing at the real part of this wave that's marking off the phase. So the guts of the wave has this incredibly fast 5/3 in this case. The speed of light is the thing that always goes faster than light in this phase that we've defined. The sum that involves the frequencies that are in play. And then the outside of this light green thing here, the group, that's the difference. It's zero right there, and is making these lines right here, which are going more slowly. Okay, they started out going nowhere at once. That was the nodes of the standing wave. But as soon as you change the frequencies at the end, or you make the thing move by just simply running very fast in whatever direction you want to be. In this case, you would be running that direction. But if I stand still and have this situation, I see the group velocity here is 3/5. The inverse of the phase velocity, which is 5/3. That's being caused by this blue line here. So I want to make sure that you see that we make two charts of these things. First of all, the space-time graph that has space and time here and keeps track of the wavelength on the space axis and the period on this axis. And there are 2 things we're worrying about here. The group, which is marked in green, corresponds to the green of the envelope of this. We're marking that as a tau, a period of the group, and there is the period right there of the group wave. In that, within that thing is an up and a down. Okay, so it's a full 2 pi evolution of whatever phase making that wave. And then this speedy wave right here, that's the phase, it has, you see, a period marked from 0 to here of tau phase, and then marked from 0 to here, tau group. And then the phase in the group, here's the group and here's the phase. Here we're looking at where that intersects here. So we mark off the distance from the 0, they all intersect right at that point, original point. But then you see now the lambda of the group is the short thing. It was the long thing in the time axis, and just the opposite, the lambda of the phase, okay, is the long thing here, it was the short thing here. So that's an important thing to realize. And you flip the 4/3 to this guy, and you get 3/4. That's what the inverse would be, which you would be looking at on this graph right here, where we're keeping track of those numbers, the frequency of the group and the frequency of the phase, just by looking at the tips of the phase vector and the group vector. So this is an easy graph to read, but this is the real world over here that's a little harder to read. In any case, when you're all done, you have these parallelograms, which if I had more harmonics, I could easily make that, this graph as complicated as that one, but right now it's very simple. I just got this thing right here. But that's as far as the geometry goes with this one, except for one thing. This is the flip of that, so the group is up here, where it was down here on this graph. Okay, so it's just a review, it's a qualitative review that I think you should have a solid feeling for before you start practicing for the exam, which is practice what we did in the last class. Okay, just to get you a feeling here. I'm going to give you different numbers. It won't be the same as those, but you get the idea. In any case, that's shown very clearly here. If you want to review with this last lecture, I've made up a slide that shows just what I talked about. A lambda group here, lambda phase there, and every one of these parallelograms that we're talking about has 2 half waves in it, and it makes a whole period of motion in the space-time. That's what this is right here, time this way and space that way. So this table has got these entries in it. In addition to the Doppler shifts, and this is just a table done the same way but horizontally. I handed that to you last time. Here's one I did to see if it looked nice. And basically you've got the velocity of the group right there, and this one you've got it first at the top of the table. And then the next one is the frequency of the group. That's right here. This is just talking about group stuff, the group waves, the green thing. And then there's kappa and lambda of the group, kappa of the group. And then tau of the group is the last thing mentioned before you get the inverse velocity of the group. That is what is actually equal to the phase velocity. And once again, the phase velocity is inverse to the group velocity. And you can see that more easily, perhaps, on this table right here. So the list of numbers for each of these things are indicated on the graph, on both graphs. You can get either all of these numbers from this graph, or you can read it off of that one. It's probably easier to get it off of this one. Okay, let's see what else. If we weren't worried about the stellar aberration angle, today we're going to show how important that really is. We would leave it out, and I did do that at the beginning of the last lecture, but here they are together. This is a miraculous trade-off between the sine and the tangent, one being hyperbolic and the other circular in each of these states. There's the hyperbolic sine, it's equal to the tangent of the stellar, and then the sine of the stellar is equal to hyperbolic tangent of rho. Okay, so the sine and tangent are married in some kind of cousin relationship. And then right in the center of these things, these two are inverses of each other. Sec hyperbolic is inverse of cosh hyperbolic of rho. But that's equal to the secant. The hyperbolic cosine is equal to the circular secant. this hyperbolic secant is equal to the cosine. It's a different number. Very seldom do those become equal. So, and then finally, this guy set right here is the inverse of this set right here. And of course, the Doppler shifts are inverses of each other. So there's a dividing line of this table, and there's one thing on things on this side, and they're inverse in corresponding boxes. Now, whenever your Doppler shift is what it is, in this case, we're talking about a Doppler shift of a factor of 2 from, well, let's just make sure I'm talking about this thing when I show you speed so often here. What I've got is the, well, look at this graph right here. What I've got is the 600 doubled on the right side, and the 600, that's where the 600 used to be a number to replace, because I'm using 150 terahertz units. Here, the 1/2 of that instead of 2 times that is this box right here. So this is the construction we did last time. Just for our reference purposes, we're going to now take that into the quantum realm. Okay, let's see if there's anything else, and this is time to ask questions right now. Just showing, once again, the geometry of the thing. And the ratios of these things turn out to be slopes, which are also hyperbolic functions, usually very simple relations there. And then you put the two together and it's kind of a mess, so I won't dwell on this particular figure right now, but you can go back and when you're doing the study of this. And then, of course, this is the one that just does the trigonometry. So you can play that one and get the values of the functions recorded for various cases. And once again, if this guy right here is rational, then all of them are rational. If this one's a rational root, then the others are all rational roots or rational numbers. So there is a nice thing when you have to teach this sometime in your future, you get to use fractions instead of decimals. You don't have to worry about the decimals, so you can have the students concentrate on the actual physics that's going on. Okay, anything you can think of to ask questions? This is a practice one. You might just start off and see if you can do it and make all of the things that we made. And I don't actually finish that one completely, but here's where that particular slide is. So I'm going to give you a blank table like that. I'm deciding whether I should even put these things, make this blank. Okay, and you're going to fill that table out while you're doing the geometry. Okay, so be prepared to do that. That's the final exam. That's it. One problem basically, but lots of parts, right? Okay. Now, it's time to derive this crazy stuff they call quantum. And I'm going to go ahead and use both of these pictures here. So here's the basic idea. The basic idea is that we've always said in this class that the mysterious part of quantum mechanics comes from something inside of the matter, something that is like a heartbeat. And that is what we've been calling phase. So the basic idea is to look at these two guys right here. The frequency associated with the phase, that heartbeat, how fast is that heartbeat? Turns out it's horrendously fast. And the kappa of the phase, that's how many kinks this wave makes when it has this frequency. And it's horrendously large. So for everything that we talk about, except the example we use. The example we use is in the terahertz. But if it was radio waves, it could be in the kilohertz. It doesn't matter. Light doesn't seem to change its nature as you go to extraordinarily high frequencies that we were seeing from astronomical objects. And, well, Hadron Collider is a good example, but it's nothing compared to what's going out in various nebula and galaxies. So anyway, here is the value in rapidity terms of the two things that we are going to play with right here now. New phase and kappa phase, and we're having a base number b, which we wrote in a couple of places over there. In other words, the radius of the main circle as seen by the source where the lasers had the same frequency, and it was 600 terahertz. In any case, that Koch rho is for sane speeds, that is the speeds we deal with in our own lives. Where if you go much faster than the speed limit, you get charged with Doppler shifts, charged by something that takes a Doppler shift of you going along above the speed limit. Anyway, the basic idea of this is thinking of u much less than c, okay? And I'm very safe in saying that I can replace this phase function here with just the first two terms of the Taylor series or concurrent series of hyperbolic cosine. Hyperbolic sine is even easier, just like the linear sine is just simply equal to rho itself times whatever the outside parameter was. So this is all I need to get started here and make some connections. So talking about low speeds, and the other one that I'm really interested in, we have to mention this guy right here, and that's our group velocity. That is the velocity, that's the classical velocity that finally quantum mechanics of any object should yield and be observable. The thing that's not observable directly are the things that involve the heartbeat. So the mysterious stuff that Newton, no idea about, got crazy about when he saw light doing funny things. He called the light going crazy, having fits. It's due to this heartbeat. But this guy right here, again, it's just equal. It's the ratio of u to c. This is the relativity parameter, beta, that appears in the old-fashioned notation here. This beta is just rho at low speeds. So rapidity and beta are equal at low speeds. Hyperbolic sine is very close to rho, and that's equal to the relativity parameter beta, which we won't mention much, but you can see all these formulas in ordinary descriptions of relativity. In any case, what I want to do is I want to mix these two, so I notice that the new phase here could be rewritten very nicely, when I can replace the rho squared here with u squared. But I got to put a c squared in the denominator in order to do that. Okay, so there's my approximation for new phase at these low speeds. And we can carry that another distance and take care of the kappa phase, the Kaiser phase, the k vector phase, with, if you add the 2 pi onto it, but we won't. We got enough clutter here as it is. This again is just a single function, single unit power of the velocity u. Okay, that is the standard letter used in almost every relativity treatment. And the thing to notice is that both of these resemble the formula that we derived at the very beginning of this class, just playing with superballs, and we came up with 1/2 mu squared. If we're willing to call m this thing. Well, that's going to take being careful with units. The thing that you see on the extreme upper right-hand corner there is a reminder of what we're talking about, inverse seconds for this frequency, and then inverse meters for the thing called kappa, and it's c kappa we're interested in, so there's c meters per second times 1 over a meter, that is also inverse seconds. So this B being equal to nu A or CK, and that's always going to be in units of inverse seconds, frequency stuff. So, looks interesting that these two would be equal. Two things that we know and love, namely good old Galilean momentum, resembles m mu if you set this thing equal to m. And if you do the same thing over here, if you set this thing equal to m, gee, that's it. Now you do really, in order to make this kosher, have to add a scaling factor. And the scaling factor that we're adding here, I've used the letter H because that's the letter that Planck used. He's doing his first look at the statistical and thermodynamic distribution of random light at various temperatures. So that right there, that thing that's going to be joule seconds or Newton meter seconds has to be put in, and we have to make sure that the units match. But you can see what's happening. I have once put this in, then I'm really talking about, and this is the mass that I really want, it's giving us just what we started this course with. And this HB is mc squared. So that B that we've been plotting in our graphs, if you put the right scale factor onto it, is what you know, the most famous formula in all of physics. Right? Not the only one I can think of that would be more famous. Might be this one, but probably not. This is the one that everyone writes in the, if you see formulas on inside of a urinal bathroom, in a men's room anyway, I don't know what the women's room has, but very often if you go to places like MIT, Caltech, and you see equal mc squared. Okay, so this is famous. Even if you got to give them credit for this 1905 discovery that is publicized by Einstein. Other people had thought of it, Poincaré was onto that. But the thing that you really have to worry about is that this is a very approximate thing. Have we just gotten a lucky coincidence here? Is this just a cheap trick that we're pulling here? It certainly looks good, but is it going to work out when I use the real thing? And the real things are these guys down here. So that's the thing. We have to try to use the exact new phase, not this approximate new phase in our discussion. So that's what we do. We go ahead and take the new phase at its word. That is, we take a hyperbolic cosine of rho and use the HB that goes in front of that, which is mc squared. So this is where we get the most basic formula of relativistic mechanics. And that is total energy. This apparently is total energy. And it's mc squared blah, 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 blah. That's mc squared hyperbolic cosine. So we've got Planck shown two pictures of him. One is, I guess, after a night on the town, and then much later in his life. He is famous for getting Einstein to come up with this. And as I've mentioned before in this class, he thought that his hypothesis that E would be equal to H times a single frequency, not omega squared, was really worrisome. Now, what we have to do here is we will have to replace H with H times some quantum number. So we're talking about the lowest quantum state here. And we also have to realize that the energy density associated with light, now I'm going to give you some references and links to our older website where we discuss this in more detail. But the basic idea of having this E squared equal to this Planck constant times a integer, quantum integer, times this quantity we call new phase is the exact thing that we need for what we're doing here. And this also will be motivating the thing that you learn first of all in your quantum class, is that you in order to get things that you're actually going to measure in most of the experiments, you need to work with a psi star psi. And for this particular case, that psi star psi comes out, if you scale it right, to some normalization, which may or may not be actually equal to the quantum number that you're talking about in the E squared. And this is where I say big worry for him. Maybe the reason his hair is standing on end is he said, my gosh, I really screwed up. My energy formula should be nu squared. But the answer is no, it shouldn't be. You got it right the first time. But it took a long time to show that that was really a thing. And we sort of mentioned this in the beginning of the review chapter when we got to the study of phase. I mentioned that the resolution, and I'd say dirty secret, is that the electric field, the N that we're talking about here, and nu phase are all frequencies. They're all frequencies in this level here. And so this is quadratic in nu phase if you really read it out. It is a quadratic expression. It's just that these guys are measuring a frequency of counts. This is the probabilistic part of this coming out as we measure counts. And I'll show you a link to something that makes a little bit more clear discussion of that. So we're doing real well when it comes to this first part of our discussion here that involves nu phase. But what about kappa phase? Kappa phase is a whole nother problem. This guy right here, and we're going to use the same front end, we're going to put an HB times a hyperbolic sine. That means MC squared times a hyperbolic sine. Well, it turns out what that is HC kappa. We have to put an extra C on this one. But what the heck is it? And you've got to realize Einstein has his idea where he makes the energy thing work pretty well. He kind of halfway writes down what it took another, well, it took until 1921 for this other thing to come up. But in any case, you can see what's going to happen here is that we're talking about kappa phases, this hyperbolic sine. We have discovered what is C times the momentum. P being momentum that we talked about so much in this class whenever we were working with the Super Bowls and the collisions of cars and whatever. And the whole idea was that our axiom was that that stuff was conserved. Well, we've got different axioms now, and we're getting all of this, and I'll show you that they're connected fairly shortly here. But in any case, it's de Broglie coming in 1921 and saying, yeah, this is what we need to explain a number of things, crazy stuff that X-rays were doing, and the Davison-Germer experiment, and all kinds of other things were happening. So this was really when it broke this. So what we're seeing here is, I would say, a natural wave conspiracy, if you want to, the current in the political jargon. And it's not a cheap trick, it's a very expensive one. And it works. So we have to say some more things about it. But old-fashioned notation, you don't need it. It's the hyperbolic cosine and the hyperbolic sine. So where on the graph are we dealing with? We're dealing with a total energy that's due to the phase right here. That's the thing that is going to be a hyperbolic cosine with appropriate factors. And then it is a function of this thing right here, which is the hyperbolic sine. So hyperbolic sine, hyperbolic cosine, they're the drivers of the function of total quantum energy. And then they ride on a hyperbola, but they start off with a parabola. Hyperbola has a parabola, a very approximation at the very bottom. That's part of the circle too. So that takes us through all of this stuff very quickly, just to flash it up here and get the final answer that we're really interested in, and the idea of some of the formalism of the quantum theory. But let's look at what we do when we teach quantum mechanics in almost every class that exists in Europe, China, you name it. We look very close to the bottom of this thing and we throw away an enormous number, mc squared, the square of the speed of light. Okay, 3 times 10 to the 8th is 9 times 10 to the 16th. We throw that in the trash can and bring this origin up to the bottom of this hyperbola, which is Bohr-Schrödinger approximation to the dispersion function that the hyperbola would normally give. Okay, so this is what's happening here. And we also realize that there's a meaning to that gap, that MC gap, squared gap there. It's called the rest mass. So we'll come back to that. How many kinds of mass are there? Well, it turns out there's quite a number. We'll deal with at least 3 of them here and shortly. In any case, the function of energy versus momentum, that's the hyperbolic cosine squared. You can write that as 1 plus the hyperbolic sine squared. So you have an equation here for E squared, which is mc squared squared, it's mc the quantity fourth, and Cp, c times momentum squared, that gets you the right units and the right values. And it's plus or minus that. The other thing that's being covered up here is the other side of this whole story. These guys are all phasors that are left-handed. The Democrats are up here. Republicans, with their right-handed, they're hiding down here in the somewhere in the vacuum. Okay, so we cannot ignore the other side of this thing. It's plus or minus that, depending on who you're talking to, Democrat or Republican, right-handed or left-handed. They're down there symmetrically displaced. So there we are. There are the main quantities. Momentum, well, first energy, then momentum. We got to talk about this one. This is weird. But remember, if you know the Hamiltonian, you should be able to get the Lagrangian. Does that transformation that we talked about quite a bit, that transformation that involves the French school of mechanics, does that work? We're gonna try that. But before I do that, I want to say some more about the mass, this mc squared, this heartbeat that all matter seems to have. Even the lightest particle we normally work with is the electron, and its frequency is exohertz, 24 exohertz. It's huge. The heartbeat of a single electron. Put 2 electrons together and you've got something that has a heartbeat of twice that. Put a whole bunch of electrons, you've just got horrendous, you've got a heart problem. Okay, this is a heart attack. So we've got to do something about that. So
We have a question.
Yeah.
How many zeros in exohertz?
Good point.
Oh, you've got the...
Yeah, we
We'll
definitely.
have to have that on the tip of her tongue here going forward.
18. Okay, we're past peta, right? Peta, now there's a computer, right? I mean, we've had terabytes and terahertz quite a bit, right? That your good computers can do that, right? That's how high, what an amazing thing that is. We're talking peta for some computers. We haven't got to exa yet for either one, the bytes or the frequency. That's a single electron. It's one lousy stinking electron. Well, not stinking, it's beating its heart like mad, right? So you're really talking about incredible frequencies when you get 1,000 times that, or 1,800 times that, 1,836 times that, actually 6 pi to the 5th times that, when you talk about a neutron or a proton. Okay, that's just one. And it's got all that going on inside it. Is it any surprise that quantum mechanics is squirrely? There's something like that going on inside everything we do. Okay, so Here's one kind of mass that we've kind of identified here. Whatever that horrendous frequency is, divided by c squared, and you get some mass that, you know, gram, whatever, or 10 minus 26 grams, depending on whatever you're dealing with. So, we got to answer the question, what's the matter with mass? Besides the fact that it's having a heart attack all the time. And as I say, I want to shine some light on this. So, let's go ahead here and see what we can do with this. First one I can do is I can go back to Galileo and say, what did you say momentum was? It was in mass times velocity. Okay. If I go and take your momentum divided by u, don't I get velocity? Yes. Okay, well let's try that. Let's define our momentum using our new ideas for those quantities and the old idea that mass was momentum divided by the velocity. The velocity is a hyperbolic tangent. The thing that we're dealing with here that's the momentum, p, is hyperbolic sine. Oh, okay, that's looking kind of neat. I've got a tangent which is a cosh over hyperbolic sine, so I can very easily write that as hyperbolic cosine. So there's what Galileo would be happy to call his baby, the mass that goes with momentum, the factor that goes on the velocity to make momentum, hyperbolic sine, if you will, hyperbolic cosine, is on the rest mass. Okay? What are the limiting cases? As I go to Galilean speeds, I just get the momentum mass. This is what we've always called the rest mass. Rest mass is momentum mass. M, nothing funny there. But as we go to the stars and things that are really moving fast, it will go blow up exponentially with rapidity. Hyperbolic cosine is e to the rho over 2 plus e minus rho over 2, okay? This is going to be an exponential explosion as far as this kind of mass. So as you get faster, you get really heavy exponentially. The effective mass, this is Newton now. He's coming a long time after Galileo. And we learned that F equal ma. Okay, so why not define a mass to go with that really works? I need to divide, that is, I need to, what I need to do here is do a dp du, not p over u, but the differential things. We're interested in force over acceleration. That's dp dt over du dt. Cancel the dt's, and I'm talking about the derivative of momentum with respect to velocity. Okay, well that's pretty easy when you have mu as a thing, but now we've got dp as this thing, and the change is of the u, that's the hyperbolic tangent, is hyperbolic secant squared. And by the way, if you use the relativity parameter algebra, this is a lot of algebra. Here it's trivial. Okay, it's a cosh of rho, and then the sich of rho squared in the denominator, and that comes out to q of the hyperbolic cosine, not first power, q. So Newton's got something on Galileo. His acceleration mass goes as that. Limiting case, this thing goes up as e to the 3 rho divided by 2. Effective mass, that's a name that is quite a bit touted these days as we talk about the effective mass in solids. Sometimes they get it backwards, I'll warn you about that. In any case, the velocity is d omega dk, or d nu d kappa. The only difference is 2 pi's in both numerator and denominator there. It doesn't make any difference at all. So dp, now I put h d kappa dk, I'm putting a bar on the h, so the 2 pi's being canceled. I get h bar, and then I have a differential of the group velocity. Well, that's the derivative with respect to k of d omega dk. So I end up with a double derivative of the omega with respect to k that goes with that, and there's the old-fashioned formula right there, the relativity formula that has the rest mass times the hyperbolic cosine cubed. And that's pretty neat. Now there's better ways to do some of this. This is another way to write these two things, this way and this way, to derive it this way and that way. But this is really an important formula to go with something everybody knows, that even though in quantum mechanics it's wrong, V group is d omega dk. That's a common thing that you learn in the Fourier analysis of the frequency and wave vector. But what I want to point out that is going on here is we have a dispersion function that describes our energy versus the k, and so the first thing we learned is that that tangent line that we drew that came across on our diagram there, let's point it out so that you can remember that it's going to be part of the construction you have to do. The hyperbola was one construction you could do by the Thales construction, but then you could very easily draw a line from here through that point there, or through, actually it was this point right here, and I've just left this one. This is a line we didn't quite finish, the one that has the hyperbolic tangent as its distance right here. Don't forget that one. It goes from there to there, whereas the momentum goes from there to there, you see. And there's this little step in to change the momentum into the hyperbolic tangent instead of the hyperbolic sine. So this would be the what we would call classical velocity in a quantum system. But the whole idea of having a tangent right here and then a certain amount of curvature in the dispersion function, that's what we're looking at, is the double derivative of the dispersion function here, which is a little bit harder to comprehend than just the single derivative, which gives the slope of that line. The curvature is some circle that you would draw that would oscillate with that particular point on the hyperbola, you see. And that's not an exact oscillation there, but you get the idea. As we go up in energy on this dispersion curve, this radius of curvature is going to blow up, and that's what this formula is telling you. But the other thing that's amusing about this is there's no h-bar in this formula, but there is one in this one. This is a pure quantum formula. The second derivative of the thing has a very big meaning as far as the mass of something moving rapidly. But we don't have anything in this laboratory that goes that fast that we work with, so very few people see this. But you do have waves in solids with very strange curvatures, and you do have Dirac points, which there's another one down here. That Dirac point is playing a role now in almost all of the research we have in two-dimensional solids in this lab. Now, at this point, I would like to bring Newton into this argument here, because he had a complaint in his book about optics, and his book about optics was good for the time, but it was kind of missing a lot of points, and he got in fights with people like Young and Hooke and a whole bunch of other people that were working on oscillators, and made a sort of an ass of himself in the process. But in his book, he actually says that light's having craziness, it's having fits. He claimed that light was just corpuscles bouncing around, but then he says they have fits. They go crazy. They do something weird, okay? And this is kind of proof. If you look at the rest mass of the photon, it has absolutely zero. If you're talking about a single wave, 1 CW, we're talking about a dispersion function that is absolutely flat. We're talking about, for the blue light, this dispersion curve here, which is not a curve, it's a straight line at 45 degrees when you use omega and c kappa as your coordinates. But the idea that, and it could go this direction too, but still, this thing right here has infinite radius of curvature, okay? So we're talking about light having a rest mass, which is the flip of that, of absolutely zero, okay? And the other way to measure the rest mass, of course, is to go and see how far above the origin are you, and you're not anywhere above the origin. This is how far you are for this little box of light of 600 terahertz. And we'll get into how the heck you get your mind around that in a minute. But the basic idea is the curvature of this has a nice circle in there. It's quite finite. And therefore, I can give you a momentum mass for a gamma ray or a photon. Okay? And it's just P over C. And that's h bar kappa over C or h nu over C squared. And then, what's the effective mass? Wow, that's pretty obvious. The effective mass for a single photon, come back to this flat dispersion curve with its infinite curvature, and you're talking about really big infinity, just the opposite of this. So here we have three possible masses for describing a photon, and it's no wonder that Newton complained, this is total triple schizophrenia, by his reasoning of craziness. Okay. Now, what does this come out to be for the kind of light we're working with? If I have a bunch of light, I don't care how big it is or how small it is, the total amount, take some total amount of light and figure out what 600 terahertz would give me, and it ain't much. Okay, when you use that formula, you get 10 to the minus 36 kilograms. That's not very many kilograms. So, you know, actually weighing light is pretty hard. Now, what if the light has a lot more energy in it? What if it has, like inside a star, or inside a hydrogen bomb? This is something Ken Ford wrote a book about hydrogen bomb, and that was his thesis. He had to build a hydrogen bomb with the help of some guys like Wheeler and Stanislav Ulam. In about 1953 or 54, they succeeded, and he got his PhD. But he realized, and they realized, that when this thing goes off, each cubic inch of light weighs 8 tons. So we're talking about light here that's pretty fluffy, right? 600 terahertz. You don't feel the weight of that. But in hydrogen bomb, just as it ignites, and then they realized that it was going to work if that could happen. You've got 8 tons of light. It is right here. You've got hundreds of tons in all, just for a millisecond. And then all hell breaks loose. So Ken, by the way, if he got done with this, he's kind of proud of his work, and it was really fun to work with Wheeler and a bunch of other people that are really smart. But he didn't even go to the, he was, you know, everybody that worked on a thing got to go and watch it, and that meant you had to be about 50 miles away. And he didn't go. He didn't want to see it. And later, he took part in all sorts of ban the bomb things. He formed a circle with a bunch of other people around Rocky Flats in Colorado near Boulder, where they actually manufacture bombs. So he became peaceable. I give him credit for that. I would have gone. I would just be curious. And no Feynman.
Oh.
Absolutely. You know, want to see this monster. And of course, you don't want to look at it because it just burns everything you have. So that's now. When it comes to describing optical mass and energy, I would point you out to our old website. Okay, and it's you know, just gets at this question. You know, if you have so much energy for a photon, say 2.5 electron volts, that's typical. Okay, the E field do that. Then the energy is given by this. What are you talking about here? For a field to you know, have that sort of thing. What kind of electric field does that? And 7.6 times 10 to the 13th volts per meter. Well, a meter is a lot, but that's the kind of thing you have if you have 10 to the 10th photons, as you do in a good healthy laser. So these are just numbers to get used to. This is Maxwell-Planck density right there. This is the Maxwell-Planck energy right there. Those are all things that I point out to you. And this goes on to a couple more slides where you try to picture what it's like if you have n photons in a hyperbola. I mean, we're talking about a 1 photon hyperbola, with the little hyperbola is way down here. Let's get up there to 10 to the 10th or something like that. So you're pretty high up. And what do you see? These are the n photons. And then what do you see if you go by it, looking at, suppose I go by this box of photons like this, so the box looks like that. It's all warped a little bit according to these curves that we've been drawing, graphs that we've been drawing. So you have n photons, you still have n photons. That's the thing that's about this, is this number of photons is absolutely invariant. No matter how fast you go, the number doesn't change. This Planck number doesn't change, but they get angrier. The ones that are getting this way are blue shifting into you, and the redshift ones are not quite as angry. Okay? And then when you look at actually counting these things, and that's what happens, you see, is that as soon as you let the wave divorce, they go back to having linear dispersion. And then you discover that the amplitude has to transform a Doppler on the same Doppler factor, e to the rho or e to the minus rho, as the frequency. Because the amplitude in quantum electrodynamics of an electric wave is a frequency too. So Doppler shifts just like a frequency. Anyway, this is all stuff that's written up in this very old website, ancient almost website, where we talk about that. And the site of that is a little bit crowded, but when you go to this site, anything that's in green will start a bunch of things. All kinds of weird things go on in quantum mechanics, and here's where you get to play with them. In addition to what we have been doing. Okay, and then there's an outline of this whole thing. So I just wanted you to see that so that you can play with it. And there's also a discussion of wave amplitude effects, which I think is almost quite frightening for some people. We have to do an E squared, but we can put a C in front of it, or we cannot, depending on whether we want to look at a flux count rate or a volume count rate. It's going to be a square of the E's, but that's what we call psi star psi. When it's moving, when it's a moving flux like a waveguide, I tip the psi over as though it's moving. If it's a box that's just sitting there, I make it a psi that's not scripted, not italicized. And then it's just a question of how do you count up all of these things. And that's kind of neat, because what you discover is as the amplitude really does Doppler shift, and therefore the wave is going to do some weird stuff. So I wanted to warn you about that, because it is really quite unnerving, and I hope I can get it to happen here. I had it going just a little while ago. See if I can get it going. Yes, there we go. And I'm going to go ahead and flash on to this old computer here that has animations that were put in that website. So goodbye elephant for a while. Here is, I hope, the thing that we've been working with. That is the thing where the phase cuts the fast phase crossbars, and the group just marches along the things there. It's all nice and sweet, isn't it? But let's see what happens if I screw this up a little bit. Let's suppose I make the amplitudes here a little bit bigger on the left side, the thing that's going toward me. So I make it a little bigger there than the other one, and we get a very different sort of graph. And this is what's going to happen when you start playing with the bottom hyperbola. You're going to be getting Wheeler-Feynman switchbacks. You're going to get some zero here that goes along the group for a while, and then gets annihilated by this fast thing and disappears because the wave just falls below the level. But then suddenly it's recreated here, pair creation, we create a zero and an anti-zero. That's a zero that has a positive slope and one that has a negative slope. So this is continuous oscillation of creation and destruction of particle and antiparticle. Something we have not really figured out how to deal with. But that's what happens to waves. And how many people know this? I have not met but one or two. One of them was Ken Evenson, saw this on an oscilloscope, and he just got fascinated. Well, why is that? And he was really happy to see there was a simple explanation for it. But this is cool. What this is, and this I really am quite proud of, is this is an analogy to the what we call circular polarization. That's a moving wave in one direction. And then this guy right here is a standing wave. And then the next, as you go and mess it up, you get an elliptical polarization. And you can move it around, so the elliptic can be anywhere. It's a two-stage system. You should expect the kind of geometry to show up if you plot it correctly. So I wanted you to see that just for the sake of it, and then here's where you figure out how fast those things are actually going. It's the standing wave ratio determines the mechanics of this, and it also determines various kinds of crazy microwave things that you could do if you had the tools to do it and the time. And it's a neat way to discuss what we've been doing here in the case that you don't make the amplitudes equal. All right, back to what we're doing today. If I can get it off of here, I've got to do that by, I'll just leave that one running since it's needs some exercise. It hasn't been working very much lately. I need to click back to this guy and go forward a bit. And on this one, let's see if I've got to click back on this one too to get going. All right, so that's the situation we have now. I'm going to go through this rather quickly since you have seen the Legendre Transformation. That's basically what we're going to do, but we're going to start with the Lagrangian as the phase. That's the whole phase right there, kx minus omega t. Now I made a big fuss about the fact that no matter what x has been transformed to, say x prime, or what t has been transformed to by Lorentz or rotations or anything, and at the same time the k's and the omegas will be transformed by the same sort of laws, no matter what happens to that light. This phase is totally invariant. This is gauge invariance. I made a big fuss about that when we had this wall of clocks, and I said those wall of clocks, the readings on them does not change no matter what frame you get into. So it's invariant to rotations and Lorentz transformations, and it's really quite remarkable. But in any case, it's the derivative of the phase that we actually get to play with, and that comes down to something that looks like this. Right here, I get rid of the time and have a dx dt sitting there, and then we just play with that. This h bar k comes out to be our hyperbolic sine momentum. This h bar omega comes out to be our hyperbolic cosine, and with its mc squared. Trying to keep the units all according to what we did. These are the units here with the kappas and the nus. These are the units over here with the k's instead of kappas and the omegas instead of the nu. So it's just a difference of 2 pi. This one uses h without the bar. This uses h over 2 pi. So just to keep that straight. But this is such a common error, forgetting the 2 pi in some situation like this. You think, oh, well, big deal, 2 pi. But that's 6.28. That's going to ruin everything, right? So just be warned. And I've done it myself enough times. Linear phase versus angular phase. Okay. So here, what I notice is that I've got my Legendre transformation all ready to go. I simply have to plug in things to that. Now I have to use the group velocity for the standard velocity, so that's going to be hyperbolic tangent. But all the other stuff we know, hyperbolic cosine for this guy, hyperbolic sine for that one, there's the Legendre transformation, okay, and we put that together, all right, which we've done numerous times for much simpler things than this, but this is pretty simple. We get here a thing like this, which is just minus mc squared hyperbolic secant. That's cool. That's really cool, because that is what is on the hyperbola that is below the shock tray here. If this one is up here, there's another hyperbola down about here that has the minus sign. It's the same as this hyperbola, but with a minus sign. This is the anti-world, so to speak, hiding from us. And the question is, how do we make that thing? So the hyperbolic secant, of course, is present in both of these hyperbolas. And so do not forget, and I meant you to have you draw another line on this graph that goes from that connection circle right there all the way across, okay, to the point right here. That's probably a good place to stop right there, because that's where the stellar aberration is. And the idea of that is that this right here, this is minus sec. That's what a circle is. That's what the secant is. So this, the height of that right here, this is a b sec of rho. From there, from there, make sure I did that right, to there, okay? And then minus that is what the Lagrangian actually is. The Lagrangian is all of the ones we work with in classical physics is down there. So when we go to negative matter, that would become positive. But in any case, that's the hyperbolic secant right now, and that's minus the Lagrangian. So here's where we prove the stuff that we've done in this course applies very nicely on relativity. Meanwhile, the Hamiltonian is just hyperbolic cosine, no plus or minus sign. So mc squared over that thing, that's the inverse, you see. So it's the inverse negative of the Hamiltonian. Now, as we look at these tables, well, I think I can show one in just a minute here. It's another way to write it, okay? That's the Hamiltonian again, just to get it right. And there's another way to write it in terms of stellar angle. Okay, one's the cosine, the other's secant. One's a minus sign, one's a plus. And the trigonometry, the circular trigonometry, of course, is very, very appropriate for a circle. You see, this Lagrangian is just a circle, pure and simple, and that's the particular point that points at the star. And the angle here is the polar angle for Lagrangian. I've never seen anybody talk about the polar angle of Lagrangian, but it's time to start. Never too late. Okay, so this is the guy that we're dealing with, all plastered in one place. And while we're at it, we're getting the phase velocity. It's not up here, it's down there. And the de Broglie wavelength comes over here. The Broglie wavelength is sort of the inverse of the thing that was our momentum. Okay, momentum has a certain length, and then that's tangent of sigma. This is cotangent of sigma, the flip of the k vector that defines momentum in quantum mechanics. But just plain old velocity, the group velocity, well, it's just the inverse of velocity that we play with there. That's the phase velocity right there. Okay. Now, they're all scaled by b, so it's not quite the inverse when you put the scale on. But it's common in high energy physics that h and c and charge are usually of electron or proton to 1. And that makes it possible to do all this stuff. This is a real quick thing here on action. What does action turn out to be? That's where you actually look at the phase directly and write the Hamilton-Jacobi equations, which we talked about. There are integrability requirements in order for an integral of that to come out to be a good classical result. So we see once again S dot here, that's L, okay, giving us the formula we just wrote down. Okay, I think that's enough. Now I'm going to very quickly, we have about 5, maybe 10 minutes if I push it a little. I'd like to talk about when this stuff moves, when this stuff does transitions, okay? The usual thing that you'll find in any study of quantum mechanics of oscillating fields that cause transitions, you'll find diagrams where they draw two levels, and then they show an arrow going between the levels that are involved in the transition, and they either show a little waving line coming in that says you're going to be pumping this thing up to there, and then when it gets tired of being up there, it's going to decay at some rate that you try to calculate, and out goes the light. So that's called a Grothian two-level diagram. Three-level will give you Compton scattering. We'll talk briefly about that. But in any case, this is typical for almost all texts to draw pictures. And then Feynman comes along and he says, no, you shouldn't draw it that way because there's momentum involved in this light. So you better draw a vector for the particle that's going to be absorbing a photon, which is going to cause it to change its speed, and velocity rather, both the speed and velocity, to account for the momentum of this little guy here. And then when the decays, like up here, it's going to be thrown away from whichever direction the photon decides to come out. And this is the same thing, except now I'm doing the thing of hitting it with a piece of light to knock it into an excited state and also make it go faster and in a different direction than straight up. This has gone from there to there. Okay, so that's it. Now, here's a better diagram of that just uses with the construction that we've been making. We're going to be going from one hyperbola to another. That's the name of the game in electrodynamics. In fact, it's the name of the game in all of the transitions. If it's a nuclear physics, you're talking about a nucleon. Well, it's going to have a bunch of energy levels, and I meant to get out the book of the nuclides, which is the most scary book in the entire universe because it's showing us that it could really be easy if we knew how to do it to make gamma ray lasers, and I realized also that they would be making a horrible weapon. But that's all not available to us, fortunately, now. But in any case, whatever it is, it's going to have hyperbolas. This business that we've made here with these diagrams is present in every thing that we know of so far, whatever kind of matter. But electrons and protons and atoms behave very nicely. So, but basically what I wanted to show you here is our geometry being played out. And I'll show you another diagram just like this, but a little bigger. But the basic idea is that this is the hyperbolic cosine. This distance right here is omega over 2, the omega m over 2, that's halfway right there, times e to the minus rho, and that's equal to omega L. The key for this thing, which I haven't drawn here, at least I have, the m means mid-level, L means low level, we'll have an H for high level. So when we have three levels, that's the letter that's being used. So here's the mid-level, there's the low level right there. Nothing happens off of the asymptotes. You've got to have this kind of structure to do transitions. And the hyperbolic cosine is the sum of the negative exponential and the positive over 2. And there's the positive over, and there's the negative exponential over 2 times the frequency. So this ratio that gives us omega L over 2, that's this hyperbola, all right, I'm sorry, this hyperbola right here is key to some interesting things that have to do with the kinetics of all of this. Now, this is again stuff that is in the old website, and I'm just going to, well, I think since we're getting short on time, I'm going to skip this. You can play with that on your own time. This is all stuff that will not be on the test. But here I have a three-level case just to make a story that involves three levels, which is what Compton scattering does involve. But I'm only going to do a transition that involves this guy. The basic idea here is I could go from this particular state, what I could do is let a photon go, okay? If I did that, when I was originally in this state, and let's go to the next slide and show that, if I start with this high energy state that's not moving and throw a photon away, and that's a magical process. Indeed, we did our resonance ways of looking at it, but if I'm going to emit a photon up that way, I'm going to drop by the same amount of energy and momentum that the photon gave. That is, when that leaves, I'm going to be over here. And now the question gets, and this is something we still really haven't answered, is how fast does that happen? And a lot of people say that's infinitely fast. And they give kind of arguments that are really quite queasy, leave me quite queasy for that. And what I would like to show you is that this process, and I think all natural processes have some finite time that lets them carry on. It's only weird things that just involve phase. This has got phase and group involved, so it can't be infinitely fast. So here's Feynman's diagram for this particular process, where we come along with no speed and I get thrown. My energy goes up or down depending on the geometry. I end up going down to here. And so the question is, what has happened? What caused me to accelerate? I just shot out a photon, and I shot out a photon that was, about a third of my mass. I mean, this is gamma ray right here. Okay, this is really serious stuff. Most of the times the photons we do in this laboratory, you wouldn't even see it if you took a 1,000-degree microphone and looked at one of those pixels up there and the light came out. Well, that's how much of a kick you get for an atom that just emits one photon. But it's not, it's an important one. We have to calculate that. And that's what those things that I left there. But I'll give you just a takeaway point here. First of all, this is all due to momentum conservation. Now, is momentum conservation an axiom we have to put here? No, we don't. This is, quantum phase counts its wiggles, and it keeps those constant. The total number of wiggles stays constant from this guy to this guy plus the light. That is an automatic. That is, we do not need another axiom like we did in classical mechanics to start this course. It is a result of wave. It's what waves do, and so much of this is that. Now, to get a recoil formula, this is a very simple one I'm going to give you here. Okay, I use just this relationship right here. This is a piece of our geometry that we've made already. We're talking about e to the minus rho, the rapidity that we're going to be picking up there, going from this state right here, omega the lowest, to the middle. If I go to the middle, this is what is involved. I need to know, as you can see, I need to know the basic frequency, the MC squared frequency of the two objects. The red object is the lower one, and the green object is the higher one. So there's the lower one. That's an MC squared for the lower. That's an MC squared for the higher. Throw the c squared away. We just have a ratio of a mass, and then I take the logarithm of that and flip it because of the minus sign. Okay, and so what I get is this higher mass in the denominator, this lower mass in the numerator. Okay. Now, do you remember what rho is? Rho is very close to u over c. So all I have to do for low speed stuff where it's just happening within a pixel there is put u over c here, and I'll put the c on the other side. Have you seen that formula like that before? In classical mechanics we did, right? Remember the monster mash? And remember when we talked about a whole bunch of masses? lined up, and then pow, one would come off the end, then pow, another one would come, and pow, 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 pow. And then pretty soon you had the rocket ship with its payload left, supposedly, you don't pow that, and you get a certain speed. It's the logarithm of the mass ratio, right? Times the exhaust velocity. Whoops. This is rocket science. And it doesn't happen infinitely fast. It can. This thing is blowing light out. Right? Well, that's something to think about. That's something to worry about. That doesn't happen infinitely fast. If it's infinitely fast, that's a whole different mechanics, remember? So,
Yeah, we've learned.
rocket exhaust, not bullets, okay? V burnout is the specific impulse, is what they call the velocity of the exhaust in a rocket, okay? It's a logarithm of initial over final mass. And it's reversible here. It's very unreversible in classical situations. You'll collect all your smoke and put it back together, and thermodynamics doesn't let you do that. But light, yes, you can reverse that. It's totally reversible. And not only that, but you can make a whole bunch of crazy coordinates that describe all the sort of transitions. And this is in that link, and also in the text that I gave you today, Unit 8, which finishes our textbook. So I like to think about, how do you view photons, and how do you view a laser cavity that's in motion? What sort of crazy stuff does that geometry give us for the light that's inside that's going back and forth between some levels? Basically, coherent states is what the laser makes. So, okay, let's do a really high coherent state so that we can think some parts of this is classical. And the idea is that we can make a grid that does that. Now this is something else again entirely. So far we've been making our Lorentz transformations, and this is a really high frequency one, but I'm imagining some very slow frequency light coming together with some very fast, making that particular Lorentz transformation. And I'm using a formula here where I just go ahead and solve the differential equations that go with the velocity is equal to hyperbolic tangent, and calculate this. And what I would like to do is see what kind of coordinate system do I get when, well, first of all, the rho is a constant. If I make a constant rho, so the thing just has a certain speed, maybe high speed, because of this really high frequency stuff and this really low frequency stuff, it comes out on a straight line. But what if I'm over here turning the frequency up and down as time goes on? I get a wiggly line, but here is a case where I raise the frequency linearly and drop the other frequency also linearly. So I start off with the two infrared beams and coming out down here, and I start taking the, this one is the, I start with an infrared beam here and a big heavy X-ray here, and I drop it down into lower and lower frequencies at exactly the same rate that I raise them on this side. So this is just an accelerator that's going to produce, turns out it produces a hyperbola. That's kind of neat, if the rates are nice and constant. So we have constant rho here, here we have constant acceleration. So I have an Alice and Carla situation. These are Carla chirping down, and here's Alice chirping up. Chirp's what they refer to when they rapidly change the frequency. And the result of all of this at midway here is a hyperbolic path. So that's a way to understand the mechanics of something traveling at a constant acceleration, and I mean relativistic constant acceleration. And there's a little bit of a scaling that has to go on here. There's Carla's light waves coming up, and there's Alice's coming up in detail, and you see producing the hyperbolas that we got, but these hyperbolas are turned on the side as x versus time. A little bit different than what we've talked about for those. Not to put too much on this, the hyperbolas we still haven't drawn, and I'm not requiring you to do it, but coming out of this 2 here is a hyperbola that comes right up through the tip of that and goes off and asymptotically approaches the light cone from the bottom. So that hyperbola is the momentum hyperbola. This is the energy one. Don't forget that that's always there. So this is a case where you have x versus time hyperbola with the x varying hyperbolically according to some pretty simple formulas. And this is an animation of that. And what's really amazing about this is this has an event horizon. Every curved space, and this is a slightly curved space, has an event horizon. So this all has to end, and there's nothing on the other side of this experiment. Of course, you can walk across this event horizon. You can't do that very well in the black hole. But anyway, this is the simplest thing I can think of to get a feeling for how that's going. So here they go, ship A, ship B. Ship A being Al, ship C being Carl, and ship D being Don. And I don't think we're running Don right now, but we are running Al, Bob, and Carl. In any case, Don would be really accelerating pretty fast toward the end there. And that's where they all share a time, and they all feel like they're not changing distances between. There's all kinds of funny things that happen in this. So taking relativity to acceleration is not a trivial matter at all. And with that, I am going to end this class and hope you make use of it. First of all, in the final, but secondly, your actual work later on. Thank you.
Thank you.